all you intrepid people ready for weather. So let's pick up where we left off. Any questions before we close? The last thing we talked about, this is really super cool here. You know, all our food. The ocean field pay. And F is algebraic. So any algebraic extension, no matter how big, then P the closure R and F is also equal. This is a big theorem. So like a little diagram here. Here you have a proof domain R, and there's this quotient field, and you have some algebraic extension here, and T is the other closure of R and F. Then this is also that's kind of a group that will solve. So why is this true? What we need to do is we need to show for all well, there, you know, um, start this over again. I didn't set this up right. So, um, okay, so what we're going to try to do is we need to show T localized in is a valuation. So if we show that T localized in is always valuation domain, of course that means that T is proofer. So let's let M equal contraction of N R. Now, what do we know about M? Well, since N is maximal, it's prime, and so M has to be a prime ideal of R. So let F be, or let U be a non-zero element of F. And what we want to do is we want to show that U or U inverse is in the N. It's the end. Let us consider, well, since U is in F, U is a root of some polynomial equation. how do I know this? Well, notice that U is in the quotient field here. So, and this is algebraic over K, right? And so this actually has to be, a root of some, notice I didn't say monic, has to be a root of a polynomial equation over Rn, because in fact, well, of course, this is constructed by being the integral closure of, R and F. And so an arbitrary element, has to be a root of some polynomial equation. Now, what do we know about this? Is evaluation domain. So let me be more explicit and say that U is a root of let's say R0, R1X, R2 squared plus Rn Xn. I claim that I can assume at least one Ri is a root. Somebody tell me why that's true. How can I assume that at least one of them should get that? My key here is this. Right? These coefficients come out of the valuation domain, are localized in, just read the values, right? And let's suppose this one is minimal. Not unique minimal, there may be multiple ones, but we'll just pick one that's minimal. And that means that our polynomial factors like this, well, in other words, I can pull out that Ri and right, because that's the great thing about evaluation domain. Really, all you're saying is one of these has to divide the others, right? Again, notice this also is a true power series, right? Notice this has a unit coefficient. And so, U is a root of a polynomial equation over Rm, which is quasi-local. Why? Because it's localization is maximal ideal, so no problem there. And infinite close. Why? because R is proof for domain, and any localization, in fact, any opening part of domain, and hence it close. So either or inverse isn't Tn, right? Right.
Question.
Mm-hmm.
Why did you say U is a root of some polynomial equation of R sub m? Where did R sub m come from as opposed to K, for example?
Well, this is almost K in a certain sense, right? Because you turn everything outside of the maximal ideal into a quotient. So how can we do this?
And you're using the fact that F is an algebraic extension of K, right?
Yeah, that's correct. All right. Okay. Yes.
So in that theorem, where we showed that if we have a quasi-local integrally closed domain, and an element of the quotient field is either U or U inverse is in that is in the domain if it's a root of a polynomial with a unit coefficient. But here U is a root, or U is an element of not the quotient field. So really we should place Rm with Tn in that sense.
Yeah.
Okay.
Yeah. Okay. Let's look. Oh, this is really more of a reminder. So I'm going to go through we talked about this a little bit, but I need to add a bit more. Let me give you this first theorem. I thought I had given this to you before, but I've been burnt on that before, so let me just make this quick. This is kind of transitivity of integrality. Let R and T be rings. And U an element of a ring containing if U is integral over T and T, the ring, is integral over R, then U is integral over R. So this is transitivity of integrality. If U is integral over big ring and big ring is integral over smaller ring R, then U is also integral over the smaller ring. So let's write this down. Suppose since U is anything. Over T, we can write U n plus P n T sub n minus one, U n minus one, T one, U, zero, zero, with, I hope my effectives suggested T i's T. So now consider we'll call it M. T1, T n minus one. And this is a finitely generated R module. Because each of the TIs is integral over R. So you can kind of deductively build this. This is finitely generated, this is finitely generated all the way up to U, which only requires these TIs, shows that that's finitely generated. Hence, U is integral over R. Okay, any questions on that? Okay, after that reminder, let me give you a list of properties that an extension of rings may or may not have. And these are actually kind of important properties in the theory of how prime ideals behave in extensions of rings. That's one of the most important things that you can have actually is possible properties. Extension. Extensions of commutative rings. And you may think that I'm freaking out here because I'm writing down these random properties here, prime ideals, but it's going to link back to integrality. We say R inside T line over and sometimes I'll just write that if given any prime there exists a prime ideal Q and P such that Q intersect R is equal to P. And we say that the prime P is lain over by Q. Now, of course, given any prime ideal in T, when you intersect it down to R, you get a prime ideal. What this says is given if you start with a prime ideal down in R, there is something that lies over. Can anybody give an example of an extension that is not lying over? That's a great idea. If you look at, for example, Z inside of Q, right? Certainly zero is laying over, right? Because zero is a prime ideal in Q, right? But there's no way that, for example, the ideal generated by two can be laying over by an ideal in the field, right? So in particular, this definition is non-trivial. There exists extensions that are not laying over. We say the extension. Which one am I going to do first? Yeah. Two. We say R inside T is going up GU if given primes P0 inside P1 and R and a prime Q0 in T such that Q0 intersect R is P0, then there exists a prime Q1 in T such that, number one, Q1 contains the original Q0 and Q1 intersect R is equal to P1. Yeah, that's a mouthful, but the concept is really not too bad, because here's my little diagram going up. So here you have this chain of two primes, P0 inside of P1 at the R level, and you have this magical prime, Q0, that contracts when you intersect it down to R. This is at the T level. When you intersect it down to the R level, you get that. Going up means that you can go up the ladder just like the P's do. You can find a Q1 contained in this that intersects down to P1. And this is how you go up. I hate this kind of question, but I'm gonna ask it anyway. What do you suppose comes next? What am I thinking?
Going down.
How about, right? Can you go down the ladder? Three. We say R inside P is going down. I hyphenate one of them, not the other. If given primes, P0 inside P1 inside R, and a prime Q1 in T such that Q1 intersect R equal to P1, then there exists a prime ideal Q0 in T such that Q0 is contained in Q1 and Q0 intersect R equal to Q0. Right. Wow. So this is just going down the ladder. So again, you start at the R level here, but this time you have a prime up here that lies over the bigger one. Call this one Q1. And this allows you to build a Q1 here that lies over, not a Q1, not that, a Q0 that intersects down to P6. Right, okay, so far. And the last one, last property that I'm gonna talk about is we say R inside P is this is, I always struggle with this terminology a little bit. This is called the incomparable property. It would seem kind of strange because R is contained in T, but when you say incomparable, you're talking about a property of prime ideals. Sometimes they say R inside T has the incomparable property. Or E. And what does this mean? Well, this means if given primes, Q0 and Q1 and T such that Q0 intersect R is Q1 intersect R, then Q0 and Q1 are not. Well, in other words, what this says, if you have, here's the R level again, if you have two primes that intersect down to the same prime at the R level, these are not comparable. And I guess, be careful, I should probably write that, because you could say, oh, Jim, what if you pick the two primes to be the same? And then, ooh, wouldn't my face be red? So let's assume that these are different primes in the first place, right? Now, let's see, how much do I want to spoil for you here? So here's kind of why are we talking about this in tandem in the ground? Well, it turns out that, of course, I think we can all see that lying over might be important, right? When all your primes are laying over by a prime from a big ring. Can anybody think of, a ring extension that's always lying over? Or like a whole family of extensions, right? Not just, oh, look inside. Well, of course, any ring inside itself. Yes,
Polynomial extension.
good, that's right, polynomials. So another example here. Polynomial extensions. Are always lying. Because at the R level, suppose I've got a prime ideal B. What lies over it?
Yes.
Well, actually, both of these primes lie over it. But these primes are actually comparable. Right? So actually, this example tells us more. Polynomial extensions are always lying over, but apparently they're never inc. As we're going to find out, so I guess I will spoil a little bit of fun for you. If you have going up, it is always lying over. So if you have an extension going up, that property will apply lying over. And here's why this comes up now. Extensions that are both going up and inc a large class of anybody know a large class of extensions that have both those properties, both going up in ink?
Integral extensions.
Integral extensions are always both going up in ink, and we're gonna prove that. And why would that be important?
Things like dimension, full dimension are preserved.
That is correct. If you have an extension that is both going up in ink, we're gonna prove that as well. The curl dimensions are the same. Right, and so that's, so in particular, what we're going to see is when you have an integral extension, the curl dimension is always the same. So go from here to an integral extension of it, it has to be the same dimension, which is kind of an exciting theorem. So let's, before we can do any of this, cool stuff, let me, give you a couple of theorems. I'm going to give you two theorems that recharacterize both going up and ink. So I'm gonna do this way. I'm gonna do these at the same time. I'm gonna write up the theorems first without proof, just so we can just bask in their beauty for a moment, and then I'll actually prove. So theorem. 512. Let R inside T be rings. The following are equivalent. Number one, going up holes. And number two, here's kind of something couched in terms of multiplicative sets that might be useful to us. If P is a prime ideal of R, and S is the complement of this prime, so it's the multiplicative set that's the complement, and Q is a prime ideal maximal with respect to the exclusion of S, prime ideal maximal with respect to the exclusion of S, then its intersection with R has to be precisely P. There's a similar theorem, characterization, for extensions that are ink. So there are four probably. Same setup with commutative ring of identity or an extension of. Following are equivalent. One, ink holes. So the extension has the incomparable property. And two, if P is a prime ideal, and here, S is again the complement of P, and Q is a prime and T contracting to P. Say, Q intersect R. P. The T is maximal with respect to the exclusion of S. or the Q is. Now, before you worry too much, S is a multiplicatively closed subset of R, right, by definition. But of course, any multiplicatively closed subset of R is also a multiplicatively closed subset of T. So this, I am correct in saying the Q actually is a prime ideal on T that is maximal with respect to the exclusion of S upstairs. So you see that there's a similarity between these two here. Going up, this is couched in terms of, if you have a prime ideal that is maximal with respect to missing the exclusion of S, where S is complement P, that prime ideal must contract P. And on the other hand, if you have a prime that contracts to P, then it's maximal with respect to the exclusion of S. Alright, so let me rip off a corollary before we get into proving this stuff. And I might even have some room for it. Corollary. Any extension that satisfies going up, as lying over, right? And the proof, of this one. It's the media for the step right here, because, suppose you have going up. That means if you pick any prime ideal, words, there's a prime Q that contracts to it, right? And so there you go. So it's immediately going up gets you lying over because of the statements. Okay. Any questions on that? All right, let's prove them in order. Let's do the first one, the statement about the equivalence of going up. So for 2 implies 1. So we assume that crazy stuff about Q contracting to P, and we want to prove that you have going up. So suppose P0 inside P1 are primes. And let's see, we're trying to prove going up. So I need to have a prime that contracts P naught. Now we have to be able to lift this up to some larger prime, so we have to go up from, what do we have so far? Q naught. Intersecting down here. So somehow I've got to build this up to a prime P1 that lies over Q1. First observation is if S is if S is the complement of P naught, then if you look at Q naught intersect S, this is has to be something else. Let's let S equal R minus P1. Okay, so I want to make that to be the smaller set, actually. Notice that what can you say about Q not intersect S? Well, notice that if you intersect, so notice that Q not intersect R is P not, right? And so that means that Q not misses the complement of the smaller ideal, right? So S is actually outside of P1, right? But the intersection of Q naught and R, that's P naught. So Q naught has to miss, in fact, it misses the complement of P naught, so it certainly misses the smaller complement of P1, correct? So this is empty. And so, as you might suspect, we can expand this to a prime ideal. Q naught to a prime that is maximal with respect to excluding S. Right? So we grow this prime to one that is maximal with respect to excluding the complement of P1, and by assumption, what happens? What is Q1 intersect R? It must be P1, right? By this assumption here. So we have built what we wanted to. This Q1 contains Q0 because we expanded it. And by assumption here, we grew it to miss the complement of P1. So when I contract it back, it should be exactly P1. So there's that direction. Everybody okay so far? Okay, well, what about the other direction? For the other direction, let's let Q be maximal with respect to the exclusion of S. Let Q be maximal with respect to exclusion of S. Which is the complement of P and R. So we can assume going up, that's our assumption here. So we need to show Q intersect R is equal to P. All right, going up. So certainly we know that Q lies over some ideal. So here's what we've got. And we know that Q must lie over some ideal, some prime ideal. And this prime ideal must be contained in P. Why? Well, what do we know about this? We know that Q is maximal with respect to the exclusion of S. So in particular, Q excludes S. So whatever I contract it to down here has to be inside of this ideal, right? Because it can't hit anything in the outside, so it's got to be on the inside. So what do we have here? Going up gives Q1 and P prime such that Q1 intersect R is equal to P. Right? So going up allows me to build this thing here. Okay. So this thing lies over P, and so in particular, and this is maximal with respect to this property. Q1 with respect to missing S.
Max value of Q.
Thank you. With respect to missing S gives Q equals Q1. And so, right, so Q intersect R is equal to. And there we go. As you might guess, the proof of the other one has got kind of some similar elements in it, and we will go over that next time. I think this might be a sagacious place to plug right now. Yeah. So. Okay, any questions? Questions? All right. Well, I will see you folks on Wednesday. Oh.